In this section, our goal is to calculate the area underneath underneath the graph and above the x-axis. Here's a picture of what I mean by that in an example. If we have a really basic function like f of x is equal to 3, and I want to know the area between 0 and 10 that's underneath the graph but above the x-axis, then we have a fairly straightforward question to solve. It becomes a little bit more difficult when f of x becomes a curve and you need to figure out the area underneath the graph and above the x-axis. And we'll get to that in a little while. So again, we're trying to find the area under f of x on a closed interval. In this case, it's pretty easy to find the area because it's a rectangle, and so you have length times width, 3 times 10, and you fairly quickly get an area of 30. If it's a curve, it becomes more difficult. Let's take a look. So although this curve is a little bit more difficult, we can still calculate it, and we do that by building rectangles, by estimating it at least with some rectangles. So the first thing I do is I divide AB up. I take this interval and I divide it up into a bunch of intervals, smaller intervals, subintervals, each with just the same width but a small difference of x. So if I have delta x in here, then my next point is a plus delta x, and then if I add another delta x, I end up with a plus 2 delta x, and I keep doing that until I get to the end point, which is a plus n delta x, assuming that I've used n subintervals. And then I start to calculate rectangles, so I use each of those subintervals to create rectangles. And now I have a few choices of how to construct these rectangles. If I construct them with the right endpoint, so if I go to here and construct using this right endpoint, I have a rectangle that looks like this, and then another rectangle that's like this, and like this, and like this, and underneath. And if I continuously use the right endpoints, I get a graph that, or an estimate that looks something like this. So it's above on some parts and below on some parts, and I hope those kind of even each other out. If I construct a different rectangle, let me go back, and I take the left endpoints, then my rectangle will be a little bit different. So now I'm above, oops, that one's above, that one's above, and if I added these rectangles up, again, I'd have some that were below and some that were above, and I'd hope that my overall was pretty good. And another thing that I could do is I could take the midpoints. So let me clear this graph off. And if I were to find the middle of this one and use the midpoint, then this will have some below and some above. And I'd have this graph, and then I'd find the midpoint of this interval and use that to construct my rectangle, and you'll see again some below and some above, and I could continue to construct all the way across all of my rectangles based on the midpoint of each of these intervals. So you can use the right endpoint, the left endpoint, or the midpoint. Once I've constructed all my rectangles, then I can find the area of a rectangle fairly easily. So my last step would just to be multiply the length and width of those rectangles and add them up. Let's use some technology to show how this works. Okay, so this applet allows us to take a look at right and left endpoints and how making more rectangles is actually a good thing. So I've got a function, a downward facing parabola here, and this is currently showing the right endpoints. So there's a right endpoint rectangle, and here's your right endpoint at 12 rectangle. And I just have two intervals right now. If I increase this to 10 intervals, then you'll see that you get 10 subintervals. So it's divided 12 because it was from 0 to 12 into 10 intervals of 1.2 each, and it's calculated the height, and now it's adding all these up, and you can see that the total sum is about 45. If you go to an even bigger subinterval and divide it into hundreds, so now the delta is getting even smaller, you can see that your blue area is getting much closer to the correct value under this graph. If I go to 1,000, then it looks like it's zoning in on about 45.6. If I go back to my two intervals, but now I look at it from the left, so it's using the left endpoint and creating a rectangle, and the left endpoint and creating a rectangle. Right now the area, the pink area, is 38, but again, as I increase, I get to 45 because some are above and some are below. I go to 100 using the left endpoints, or 1,000, and I start to zoom in on the same values that I saw with the right endpoints. In fact, if I do the left and the right endpoints, you can see that they are really close at 1,000. They're actually really close at 10 to each other, but they're not a good estimate, a perfectly good estimate, as I lower this, like we saw with 4 or 2. Okay? Okay, we talked about that we can use different rectangles. If you use the right endpoints n times, you use r sub n to show that you're using the area of the right endpoints. If you use the left endpoints, L sub n, and if you use the midpoints, M sub n, to show the total area of the right, the left, or the midpoint rectangles. Let's just take a look at r sub n. And the same idea will apply for the other ones as well. But you've got a function when you calculate the area of each of these rectangles that you need to calculate the right endpoint. So a plus delta x is the height of your rectangle, and you have a width of your rectangle of delta x. Then you go to the next right endpoint, which is f of a plus 2 delta x, and the width of that is delta x. And you just keep doing that until you get to the last one, and the last one is a plus n delta x, and the width is still delta x. You can factor out a delta x, and you'll notice that what's left over is f of a plus delta x plus f of a plus 2 delta x, and all the way until the last one, f of a plus n delta x. And so you get a formula for the sum of the rectangles using the right endpoints, known as the right sum formula, because you have the width, which is the same, times the heights, all added up. Let's take a look at actually doing an example of this. So we're going to calculate the right sum of the area using 4 rectangles. That's what the 4 is going to indicate here. And we've got an a and a b value of 0, 4, and I've got a function of f of x equals x cubed. So, step 1, I need to know my change in x, and I need to know where all my right endpoints are. So the change in x is how far have I gone? So that's b minus a over 4 intervals, over n number of intervals. And in this case, 4 divided by 4 is 1. So I go from 0 to 1, 1 to 2, 2 to 3, and 3 to 4. And my right endpoints, therefore, are going to be at 0 plus delta x. So that would be at 1. And then at 0 plus 2 delta x would be at 2, at 0 plus 3 delta x would be at 3, and 0 plus 4 delta x would be at 4. So those are the locations of my right endpoints. If I were doing left endpoints, they would be at 0, 1, 2, and 3. If I were doing midpoints, 0.5, 1.5, 2.5, and 3.5. So as you can see, the process works very similarly for each of these. Step 2 is going to be to use the R sub n formula to calculate the sum of all of these rectangles. And so the R sub n formula looks like this, and now we fill in some of the information we know, like we're finding R sub 4, our delta x was 1. Now we need to evaluate our function at 1, and at 2, and at 3, and at 4. And our function was y equals x cubed. So we get, which gives us an answer of. If we used the left endpoints, we would have done 0 cubed plus 1 cubed, 2 cubed, and 3 cubed, and we would have only ended up with 36. So when we're only estimating with 4 rectangles, we don't get a very good estimate. 100 with the right and 36 with the left, those aren't very close. So it does matter which one you use, and it would be nice if we could make that n value a little higher than 4 rectangles. Let's check this with some technology. Here's our check of what we just calculated. So right endpoints with our function f of x equals x cubed. So the first rectangle, second rectangle, third rectangle, and the sum of the rectangles is 100. And as I said, if we had done the left ones, you would have seen only 36 because it would have taken 0 and 1 and 8 and 27 instead.